Yeah, thank you very much for the invitation and thank you very much for the introduction. I'm very glad to be here this time of the day where it's time for me to wake up, coming from Europe, so it's good to wake up before your talk starts. I hope that's the same for all of you. As it was introduced already, we work on neuroscientific system theory. Now that's a very abstract term and people really can't relate much to that, especially not in a robotics community. So what we do, I like to rephrase as neural computing in hardware and software. We try to understand principles of neural computation and apply these to technical systems. Now that seems a great match for this session, where event-based vision really is just one aspect of what we do and what we work on. So you see that there's my group listed, there are some sponsors listed, and sadly to say event-based vision is just a small part of what we do. But I'll show you how I think we differ from what you've seen today so far. So this is a slide I often use to introduce event-based vision to my students and other audiences. You have heard this many times. Today I don't need to go through this in detail. Just look at the list of advantages that I make use of. I think this, what I think I've identified as the core advantages of event-based vision is the sparse data stream. We're getting significantly lower amount of data from a scene. We're getting very low response times. I've totally mentioned this many times. Maybe it's not 15 microseconds, but we're talking of at most 100 microseconds. It's much faster than our 30 Hertz regular cameras. And we have a very large dynamic range. So that's the advantages, and that's why I'm very excited to apply this to technological systems, to robots or other computing systems. You see the type of event data shown on the right, so you've also seen plots like this today. We're getting a quasi-continuous time signal of individual dots, individual events saying, here has something changed in the image. Now that's the background, and now we're all on the same page. This is the systems that exist today. So if you go to any of the commercial vendors, so any labs, if you want to buy your own sensor, you will see this. These are devices that have different spatial resolutions, different properties, with or without traditional camera image. But the common feature that all these devices share is they have a USB connector. And what you do is you plug this device into your computer and you run your algorithm in your computer. Now that can be a Linux stick on board of a robot, this can be something else, this can be my desktop or a GPU-based computer. But all the algorithms we've seen today run on computers. Now my interest is getting things miniaturized, really small, getting things embedded. That's why we developed in my lab hardware systems like this, where we integrate the sensor chip and the microcontroller on some autonomous, on some self-containing circuit board, so you apply power, and the system does its operation, it does run its algorithm, everything on board, everything integrated. Either slightly bigger or slightly smaller, and you will see applications and more details of this in the upcoming slides. There's also a demo booth right next to the exit door, so on your way out or in between, you're welcome to come by and see all these systems in operation. So what is on the board in this embedded vision system? I've given you the idea already. We want to run algorithms on board of the microcontroller. So what we have is the vision chip, the standard DVS128 vision sensor chip. So 128 by 128, 16,000 pixels. But these chips directly interface to our microcontroller, where we have some background process to read in data into a ring buffer. We're not blocking any of the CPU load. So we have this microcontroller that can run custom algorithms on board in real time to do data processing. Now we have some other circuitry, there's some reset button power switch, that's what you know from embedded systems. If you flip this particular board around, look at the back side, you have quite some support electronics such as a high power motor driver, such as SPI ports or additional UART serial interfaces. You have general purpose I/O, analog digital outputs, and so on. So you have a standalone small computing board directly connected to your DVS sensor chip. Now that seems fancy if you look at it. There's a computer attached directly to the sensor. This comes with a lot of drawbacks, and the two obvious drawbacks is you're very limited in terms of memory, onboard memory. Here we have about 150, 200 kilobytes. And you're severely limited in terms of computing power. you have on the order of 200 megahertz clock rate for these advanced microcontrollers. It's a 32-bit RISC instruction, so that's fine. It's a standard processor, but it's only 200 megahertz. My laptop runs at 2 gigahertz and probably has 4 cores. So we're talking of a very different range of computing system. You also have advantages such as relatively low power consumption of the overall board compared to any Linux PC stick or especially laptops or real computers. But probably the bigger advantage is the very low latency. There is no USB anywhere in between. You have a direct connection coming from the sensor chip into your microcontroller, so you can make use of these very low latency systems. And that's what I will show to you, how we can apply these systems in, I think, relevant robotic tasks. Just as a comment, I don't see my time anywhere. Does anyone? Otherwise I will talk forever. Good.
I'll do the time.
Wonderful. So you've seen the systems. Here are certain examples of what we do. We have little robots. Those you also see standing in the back. You can show them live. We have balancing robots, we have tracking robots, and we have a robotic head. That's what we do versions, as I just asked in the question. So you'll see plenty of these. I'll talk in more detail about plenty of these projects on the upcoming slides. And just to make sure that we really all talk about the same thing, we've often seen videos like this, where I hold the DVS sensor in my hand and wave it through my office, and then we get a video like this. No, that's not true. We're not getting a video like this. The DVS sensor outputs a continuous stream of events like this, where we have certain numbers, let's say X position, Y position of the event, polarity of the event, and the time at which the event occurs. And we're getting a sequence of these events out of our sensor chip. That's the data that we have. It's not that. That is a reconstruction that we create out of this data so that we humans understand what's going on. This is not what's coming out of the sensor. It's this. And this is what we can take into the microcontroller, and we have to design algorithms to make use of that data. We've seen plenty of different algorithms. There was a session on algorithms before the lunch break. We've seen algorithms right now. I'm very excited about that big progress. These algorithms are absolutely capable, and I'm super impressed. So thanks a lot, Davide, Andrew, and all the people who've presented. I think you're coming from the wrong corner. You're all computer vision people who now go into event-based vision. You're performing well, you're doing great, but you all mentioned you still need big computers. You all, in one way or the other, reconstruct an image or a patch of an image and then do computer vision on that patch of an image. Now we can argue how much this is true, and we probably should, but it's all computer vision view on event-based systems. And again, they're doing great work. I'm coming from the other side. I'm trying differently. I'm not as good as they are, I admit this right away. But I think these are very complementary approaches, and they can benefit from each other. And especially this bottom-up, building up on single events into an understanding of the scene that you will see is much more suited for low power, low computing systems rather than patch matching or similar patch analysis as we've seen. So what do I mean with this? It's my true philosophy that I would like to take in a single event, process that event, memorize something, and then forget that event. I don't want to accumulate a time window or an n number of events window and then process that window, because then I'm going back to reconstructing images. So I'm very keen on designing algorithms that operate on single events and remember some high-level data, some high-level concept of what the earlier events have caused, but I do not want to reconstruct an image and operate on that in the ideal case. Now here's a typical example that also many people have addressed before. It's tracking a blinking light. That's really easy to do if you think about it. So if you have a light, let's say this one that's blinking at 1000 Hertz, then for us humans this is just a light that's on. We can't see 1000 Hertz. The sensor obviously sees on, off, on, off, on, off all the time. Now what I can do is I can create a memory of the last time at a given pixel where I've seen an on event. So this is a metric that's 128 in size. I remember the time when I've seen the last on event at this pixel, or that pixel, and so on. So there are time stamps in here. When a new event comes in, I can compute the time difference between the new event and the memory at that location. If the time difference is close to my expected time difference, 1,000 microseconds for continuous on events, then I give this incoming event a high weighting, a high ratio, saying this is a relevant event, this is very likely coming from my target, from my stimulus. If the time difference differs to the expected time, to 1,000 microseconds, then I give this a very low weighting. So if I'm somewhere off, I just decay, I don't take that event as meaningful. Same is true for spatial vicinity. So if I'm already tracking a stimulus, if I have some estimate of where that stimulus is in the world, the next single incoming event has to be nearby. So I can look at spatial vicinity as shown here. I compute the spatial distance between, the Cartesian distance between the new event and my believed track position. I can get a weight, a relative weight for that spatial, and I can combine those two weights into a significance, into how meaningful this new event is with respect to tracking the light, and I can update my position. I can compute the new position as a fraction of the old position plus the complementary fraction of my current incoming event. If the event is very close to 1,000 Hertz, I'm getting, and very close spatially to my current track position, I'm getting a number that's close to 1, so I believe my new event a lot. If it's far away in time or in position, this term goes close to 1 and I believe my old track position. That's all the tracking algorithm I need. And now we get the idea already. Yes, I'm creating a memory of timestamps, but that's spatially local. I'm not creating local patches that I have to compare. It's per pixel. And for every new incoming event, for every new possibly from this event or from any other event that's coming in, for every other event I can have to run this formula once, and these are lookup tables, that's not costly. I have to run just this equation once, and I can run this on a microcontroller. So Andrew mentioned in his talk earlier, yeah, we might run out of computing power per event. If we think of algorithms that are very efficient per event, we can do this on microcontrollers. So we're running at 200 megahertz. We're typically getting 100 kilo events, maybe 200 kilo events. So we have about 10,000 assembler instructions per event. That's about 50 lines of C code with no loops, with no fancy square roots or anything. But we can do quite a bit of code per event. This does not do... Question now or later?
Sorry, are you only tracking markers? I mean,
No, that's the beginning. We move on from that. Sorry, of course, this is the very simple. Tracking markers is brain dead. Okay, so what we do with tracking markers is we can have these robots that follow each other. There's a blinking light on top of these that blink at some frequency, so we can track that, and we build a robot chain that follows each other. Good. Now we have markers. Now we go beyond markers. Here's the first example to go beyond markers. Now again, that's easy. We're just tracking lines. We're not tracking anything fancy. We're putting up a line, so a pencil up here on this movable table. It's a cart that can move left, right, back, front. And we have two perpendicular-looking event-based vision cameras so that we can find out what this line, what the model of the pencil, the line is doing. And as soon as we compute the position, the 3D position of that pencil, we can move the motors to compensate for the falling pencil. Now, if you think about this, this is an ideal problem for event-based vision, because if we balance the pencil perfectly upright, then there are no events. Nothing is happening, we're not getting any input, we're not moving, everything is great. As soon as the pen starts falling, with very low latency, we get some events that correspond to the edges of that pencil, and we can track that line efficiently. And we can quickly move, so we are simply using a PD controller to move this little cart. There's no predictive control, there's nothing fancy in here, there's just a PD controller running at 1,000 Hertz, computing the desired new positions very fast because of the high-speed input coming from the event-based cameras. But now we don't have a blinking light, so it's much more difficult to find out where this pencil is. So what we do, again, that's a simple approach. We model our pen by a line. That's the light blue line you see here. For an incoming event, This one incoming event, the yellow event here, does not tell me where exactly the pan is, how it's oriented. It just says that the pan is likely to go through this point, but it might have an orientation almost vertical, it might have some angle to the left, some angle to the right, we don't know that. But if we convert this into a half space that represents all possible lines going through this point, characterized by their slope and their base, then for this one event, we're getting a corresponding line in half space. So if you think about this, you can model this pan with a line equation, y equals mx plus b if you want. If you convert this into the space of mx, slope and base, then there's also an xy in here. This is given by your event, and this is still a line in half space. So this one incoming event corresponds to a line in half space. The next incoming event, this green event, corresponds to another line in half space, and the third event to a third line, and so on. So we can do that computation for every single event that's coming in. Now, in a perfect world, infinitely thin pan and no background noise, then this will fill up with lines that all intersect in exactly one point, and that one point will give us the correct base and the correct slope. Now, in the real world, there is noise. The pan is a non-infinite width, so we're getting lines that do not perfectly intersect. So we found an algorithm presented a long time ago how to incrementally update, so we can model each of these lines as a 3D Gaussian, and if you get more and more and more, you sum up the coefficients of these Gaussians to build up a likelihood of where this point is, and you can track the maximum position in that space, so you find your most likely base and slope. And again, we do all this in a microcontroller running that pencil balancing robot. Again, it's a very simple object, it's a line. We're not tracking very complex shapes, but we're going beyond simple markers, so we're extending the system. Let me for a second detour. So we also have, Chiara mentioned this just now, we have a neuromorphic computing system, so we use these event-based vision sensors to interface through an interface board directly into a neuromorphic computing system where we do things like optic flow processing in neural networks or distance estimation. There again is a blinking light here where we can compute the angle between the robot and the light and the distance based on stereopsis. So we do this, but then again we're not looking at a single microcontroller, then there's quite a lot of computing power that we have in here. Let's go back to single microcontroller and some more fancy things we can do with that. So here is a navigating robot, and again, my background is not really robotics, so I'm not claiming that I'm building the most fancy navigation system ever. I know Sebastian Truhn and people here in this room do amazing SLAM systems. Here we're building a SLAM system very similar to what Andrew presented earlier today, a particle filter-based SLAM, where our event-based sensor looks upright at a ceiling, and for simplicity we assume the robot is driving on a floor with some structure on the ceiling, so it's a simplified problem. It's a 3D mapping, it's XY position and orientation of the robot. We're not at 6 degrees of freedom yet, but we're getting there. So we have this robot driving around, the sensor is looking up at the ceiling. For every incoming event, now we concurrently do two things. We do mapping and localization. So we use a particle filter so that for every incoming event, we update our belief of where we are in the world based on that event. And for every incoming event, we incrementally refine our map. Now, how do we do that? Let's assume we have a grayscale map of the pattern at the ceiling. Then it's pretty easy to update my particles. So each particle has a certain belief of where I am in the world. In the traditional particle filter, I will take a snapshot of that ceiling, and I can compare that snapshot, the whole picture of that ceiling, with my particles, and immediately say, this is a good particle or this is a bad particle. Now, with a single event coming in, we can't do that. If I'm here, if I'm truly here, the robot is truly here, looking at this direction, and moving, and there's an event coming in, then this one event will increase the likelihood of correctness for some of the particles and decrease the likelihood of being correct for other particles. How is that? Every particle has a believed position. Now, given my knowledge of the world, given the partial available map of the ceiling I have, the fact there is a new event coming in either matches with that map or there's a discrepancy to that map, and depending on this two, it's a binary decision, depending on these two, I can increase the likelihood of this being a good particle or decrease the likelihood of this being a good particle. So if we get many, many events, if we get a continuous stream of events, for every single new event, I can update all the likelihoods of all the particles, and eventually I have to prune them or create new particles. Now that's the localization, and the mapping is very similar if I believe, map building is very similar if I believe I know where I am, because I look at my particles, I have some estimate of where I am. As soon as I get a new event in, I can put this information into my map and therefore incrementally build up a representation of the world. And this is what you're seeing here. So again, we're playing, now we're back at the robotics mode, we're playing a bit faster than real time, because this robot is driving much slower in reality. It's exploring an unknown area in the basement, it's looking up at the ceiling as shown here, and it's coming up with a map like this where the black in the background shows the pattern that the robot finds on the ceiling. The red is its own estimated path. We didn't have overhead tracking at the time, so we couldn't find ground truth, but just the fact that this black pattern builds up consistently on the ceiling shows that the robot has a very good estimate of how it's moving. Let me stress this again, this is not the world's best SLAM system, by no means. This is running as a vision-based SLAM system on a 100 megahertz microcontroller with 200 kilobyte onboard memory in real time. This is the point I'm trying to stress. Because of the very efficient visual input and because of this processing that we do event by event, and then forget that event, we can run all these updates in real time on the microcontroller that we have. Now this is 2D, two-dimensional. We're working on extending this to 3D, and now obviously the robots for 3D that everyone's talking about these days are quadricopters. So we're starting to develop, we have developed a significantly smaller version of the embedded event-based vision system. So it's the exact same thing. There is an event-based vision sensor chip developed by Toby on one side. There's a microcontroller, 200 megahertz, 500 kilobyte SRAM on the other side, some support electronics, and an I/O port, so I can send data in and out. But I can pre-process all the vision data in real time on this system. We have a quadricopter that has 1, 2, 3 on the backside and on below, 5 such event-based vision sensors on board. There is one microcontroller with a large SD-RAM in the center of this quadricopter, that's our own development. That one integrates information from all these 5 outside-looking event-based sensors, but it's not integrating individual events. That would be an overkill for the poor microcontroller inside. These guys on the outside pre-process what they see. For example, as you see in the video now, they do line tracking in real time. That's what the microcontrollers do. And they will only send this abstract information that the red superimposed lines with an ID label, they will only send this information to the center guy that combines this line tracked information from all the other 5 and comes up with a consistent map and builds up a 3-dimensional map of space. So we're not there yet. I need to talk to Andrew and David a lot about how to do that. That's not our expertise, but we have this system and we're planning to fly. So you've seen I can hand control and fly it. We can get all the data on and off. It's all working in real time, but it's not a closed loop system yet. Now this is our current prototype. We are still going smaller. So this is where I have some systems with me. This is a micro DVS system. You see, this is a 10 by 10, 9.2 by 8 by something millimeters. It's the microcontroller. On the other side is the DVS bare die, just the silicon, not the whole packaged chip. There's a plastic lens in here. This is a very small commercially available micro quadricopter, so it's this that you can buy as a toy. If we remove the shell and all sorts of other extra load, we can remove up to 2.5 grams of weight, so that's what we can add again. Each of these is only 0.24 grams, so we can add quite a lot of our systems. And if you believe that we can get this system flying and do autonomous navigation, I see no reason why we can't this system to fly and navigate autonomously. And that's our goal for the upcoming few months. I have prototypes of all this with me, so come by at the door before you leave the room. I have 2 minutes left, wonderful, so I'll open up another box of real-time projects. We've spent some work on stereo vision, on detecting distances. And before I go into detail, same story again. This is not the world's best stereo vision system, by no means. You will be upset how bad it performs. But it all runs on microcontrollers that you can carry around and that you can run with your battery pack for many hours, which is particularly relevant for this project. So here we've developed a stereo system that should help visually impaired people who typically use a white cane today. If you see a blind or visually impaired person, they typically have a white cane to test the environment around them. So there's many drawbacks, including it's not hands-free, including you can only spot objects up to a certain height in a certain area in front. If there is a truck with an unloading bay in front of you, people bump into this all the time. They tell us that's a big problem. So they would like to have some additional device that monitors the free space in, let's say, 2 meters distances. They don't care what's 20 meters ahead, they care about the local area. So we want to build a portable device such as this that has 2 of the mini DVS, some computing power, so we're not quite there at the microcontroller level, but we have an Intel board that consumes about 100 milliamperes, so it's pretty easy to use. And we've built a stereo system that takes input from 2 DVS sensors that you will see in these slides. So we get input from these left and right event-based vision cameras, and we can match events from left and right. It's not a trivial process, so I can talk much more if you're interested how this works to get a good match. But you see here color-coded the distance information that we can extract. Now again, this is a particular good example, that's why I showed this video. It's not always that good, but we do have a very high reliability of detecting objects that are blocking nearby space. And as soon as we have the distance information in color code, then we can emit warning sounds. The easiest would be a message saying there's an obstacle, or we can produce some sound, some landscape of sound that corresponds to the objects nearby to help visually impaired people to navigate more safe. That's the project I wanted to address. My punchline is I care a lot about closed loop systems, but I don't want a big computer in the system. I think, but again, what we do in this field I think is great. There's so much progress. I think we need some of these applications to be really small, really portable, really low energy, to give out outside of this room. Because everyone in here goes, oh, that's really nice, really cool things. But as soon as you go out, it's very hard to convince industry. We collaborate a lot with BMW, with Siemens, with Bosch and so on. They're all very reluctant taking on. And I think projects like this offer one path into that domain. Having said this, this is a brief overview of what else we do in my lab. So event-based neuromorphic vision is just one aspect. We care much more, or at least as much, about neural control of robots with distributed neural systems, or navigation, grid cell, place cell inspired. There's much more. This is our lab's webpage, and with this I conclude. Thank you very much for your attention.